In this video, I will talk about group theory and chemical applications. Group theory is the framework for studying symmetry, which is fundamental to understanding the structure and properties of molecules and crystals. In chemistry, group theory provides a powerful tool for simplifying complex problems and making prediction without the need for extensive calculations. It is used for the solid-state chemistry, and it is also useful to simplify the quantum chemical applications. So molecular orbital diagram constructions for molecules is simplified by group theory. Group theory helps us to predict the degeneracy of the orbitals. And secondly, group theory is useful to predict which modes of molecules is spectroscopically active. Infrared and Raman active modes for the molecules can be determined by using group theory. Group theory is also useful for crystallography. Group theory is used in solid-state chemistry and material science to classify crystal structures. Group theory is also used for simplify quantum chemical calculations. Group theory can be used to classify atomic and molecular orbitals based on their symmetry, and group theory simplifies the hard calculations and make it easier to determine the energy levels and behavior of electrons in a molecule. What we need to know to use group theory? Simply, we need three things. The first one is symmetry operations. The second thing is character tables. Third thing is point groups. And fourth thing is using the character tables. But in this video I will not talk about using character tables. It is symmetry operations. Symmetry operations. Symmetry operation is an action that leaves the object the same after it has been carried out. We have 5 basic symmetry operations. First operation is identity, and it is represented by E. We have also reflection. It is represented by sigma, and we have two sigma. One of them is sigma V and the other is sigma H. So sigma V contains the principal axis and sigma H perpendicular to the principal axis. And the other symmetry operation is proper rotation, which is represented by Cn, and principal axis is highest order principal rotation. I want to give a very simple example. For instance, we have a water molecule, and our principal axis is from here, and it is C2 axis. N means here is that 360 over n degrees, which means that if we apply C2 to this water molecule, this hydrogen will go here and this hydrogen will go here, and after the operation we will obtain exactly the same molecule, and therefore this is our principal rotational axis, or this is our principal axis. For instance, if you try to apply sigma H, which is this one, it's perpendicular. This is sigma h. And if you try to apply it, this hydrogen goes to here and the other hydrogen goes to upper position. So molecule changes. Therefore, water molecule does not have a sigma h axis. But on the other hand, if you try to apply sigma v, we have actually two different sigma v's for water molecule. So we have water. This is our C2. We have one sigma v, and we have also other sigma v. If we apply the sigma v for this water molecule, hydrogens will replace with each other if we apply this one, for instance, and molecule stays same. So we have one sigma v, and the other sigma v includes all the water molecule, and every atoms in water stay in the same position. So I showed three different symmetry operations, and I will go with the inversion. So fourth one is inversion or I symmetry operation, and this is the C2 times sigma h operation. So first you turn the molecule 180 degrees and then you apply a sigma h. This is called as inversion operation. We have also improper rotation, and it is represented as Sn. So this operation is rotation as Cn, and n here is 360 over n times, then we apply sigma h. So another means that I operation equals to S2 operation. In order to understand and use group theory, we need to know what is point group. Point group is a classification system for molecules based on their symmetry. And point group is a set of all the symmetry operations that can be performed on a molecule that leaves at least one point in the molecule space fixed. Every molecule can be assigned to a specific point group. To determine the point group of a molecule, we use a flowchart. You can see a flowchart here, or it is called a symmetry tier here. And we can make an example. What is the point group of water? Firstly, we have to draw the molecular structure of water. We have one oxygen and two hydrogen atoms. Due to the unpaired of electrons on the oxygen, we have a band structure for the water molecule. We don't consider the electrons on the oxygen, and firstly we ask the first question to determine the point group of water molecule. So is system linear? System is not linear, therefore the answer is no. And do we have a higher order axis? The answer is no. Do we have a principal axis? The answer is yes, we have C2 principal axis. C2 means that 360 degree over 2, and it is equals to 180 degree, which means that if you rotate the molecule from here that contains the oxygen, the first hydrogen atom, this one will go here, and second hydrogen atom go to the first hydrogen atom place. So this is the case for the water molecule. So the answer is yes, we have C2 axis, which is our principal rotational axis. Do we have an orthogonal C2 to C2 or our principal axis? The answer is no. If we rotate the molecule from here, for instance, the hydrogen atoms will go to the upper positions, which means that we don't have a C2 orthogonal to our principal axis. So the answer is no for this question. Do we have a sigma h? Sigma h is simply this one. We have a principal axis here, C2, and this is the sigma h mirror. If you make the mirror for our water molecule, hydrogen atoms will go to the upper positions, so the answer is simply no. Do we have a sigma v? And I showed it in a few minutes ago, and we have a CV or sigma v, since, for instance, if you think the plane that includes the C2, and this is just a mirror, and if you apply it, you will obtain the same water molecule. So we have a sigma v. The answer is yes. And the second sigma v, by the way, here. So we have two sigma v that contains C2 axis. So the point group of water molecule at the end becomes C2v. So this is point group of water molecule. And third thing, to use the group theory, we have to know some things about character tables. Character tables is a summary of all the symmetry properties of a molecule that belongs to a specific point group. It is a fundamental tool that helps chemists to predict molecular properties without complex calculations. So this is C2V point group table. In this table, you can see the symmetry operations, and these are simply symmetry operations. You can see the irreducible representations. You can see the quadratic functions and cubic functions here. And these functions will be useful to understand whether the mode is infrared or IR active. I mentioned that these are the irreducible representations, and we can write our representations, for instance, for the water molecules. In order to use a point group table, we have to write our reducible representations to all the problems. For instance, we have a water molecule, as I mentioned, and water has a C2V point group, of course, since this is the C2V point group. And I want to write the reducible representation for the bonds for the water molecule. So I want to write reducible representation for these two bonds. And what I will do is that if bond position doesn't change, I will write for each one. But if position change, for both of them or one of them, I will write 0. For instance, if I apply the E operation, and E means that we will not do anything, and bonds will stay in the same position since we didn't do anything. I want to show x, y, z coordinates for me. So this is z coordinate, and if I apply C2 here, this bond will go to this position, and this bond will go to other bond's position, which means that positions changed, and I will write 0 since positions of the bonds are changed. And I will look at sigma v plane, which is the xz plane. So this is, for instance, x, and this is the y. And if we apply the xz plane, so I am assuming that there is a plane here. If there is a plane here, and if I take the mirror images, same thing will happen, and bonds positions will change. So the answer is 0. But if I apply the YZ plane, it includes all the water molecule, since this will be the sigma YZ plane, and irreducible representation will be 2, 0, 0, 2. So if you look at carefully, this is this thing RB equals A1 plus B2. Since if you add them up, 1 plus 1 is 2, 1 minus 1, 0, 1 minus 1, 0, 1 plus 1 is 2. And this is equal to A1 plus B2. So what you learned is that reducible representations can be written by using irreducible representations. And this is all for me today. I will make some examples, and you can watch that videos to understand the concept more deeply. And thank you for your attention.